Hi there, welcome to our Math 230 group project number 2 on the role of integration in medicine. It's by myself, Cy, Ash, and Mary Chewy. Now, you always hear that math is important in daily life, but it's not often that we get to witness or understand how it truly is applied. However, we're going to discuss how certain mathematical concepts such as integration and integration by parts can be seen and utilized in essential areas of life, such as the medical field. Specifically in the medical field, we can utilize integrals in respect to drugs as we can model how they decay in the body, the concentration of a drug in a person's bloodstream in relation to time, and more, all of which allow us to understand safe and effective dosage levels. However, let's first define our mathematical concepts that we use for medicine. Integration describes the area underneath a function over a period of time. We find this area by adding up the area of infinitely thin rectangles under this function line over a select interval. In medicine, this integration can be used to model growth or decay of bacteria or medicine concentration in bloodstreams. It can be used to calculate total accumulation of drugs, determine the rate of change of over time, and many, many more. However, in order to find the area under a function, we need to find the antiderivative of the function within the integral using an integration technique. One of the most important integration techniques is integration by parts. We can integrate by parts knowing that whatever function we are integrating can be thought of as the integral of u multiplied by v dx, all of which is equal to u times v minus the integral of u prime multiplied by v dx. We then simply evaluate the newly written out integral expression, and we can plug in the high and low ends of the interval we are evaluating for our answer. And that can be seen by this expression here. Now let's apply these concepts into a more understandable medical context. Let's pretend that we are anesthesiologists who are prepping for a 2-hour surgery. Our job is to make sure the patient stays asleep for the entire 2-hour procedure, so we need to understand how much total exposure to our anesthetic drug our patient has over the surgery from one dose of our anesthetic. We know we can model a function, f of x, which represents the concentration of our drug, with x representing hours. Now, with all these various pieces in mind, we can put them all together using integrals and substitution by parts to see if the total concentration of one dose of drugs will keep the patient sleeping for the whole 2 hours. However, before we can start to calculate, we need to know what our function f of x is. We can model our function f of x as equal to 39x times e to the negative 4x power, which, as we established, models concentration of the drug over time. Now, the last piece of information we have is a minimum total exposure level. This level describes the minimum value that our total exposure has to be so that our patient stays asleep. We know this minimum value is 2.5, so our goal in calculating the total exposure of one dose of anesthetic is to see if it is above or below the minimum value. If it is above, our patient will stay asleep for the whole 2 hours. If it is below, they'll wake up. Finally, let's put this function into our integral, which can be modeled as the integral from 0 to 2 hours of function 39x times e to the negative 4x dx, as can be seen right here. Now that we put all our medical knowledge into an integral, we can find our total drug exposure from one dose by integrating using integration by parts. We can first pull in front of the integral, then define each portion of the equation. U is equal to x, so our u prime is equal to the derivative of x, or 1. Then we conclude that our v prime is e to the negative 4x. We now have to antiderive e to the negative 4x, but using our knowledge, we know that to antiderive e to a power and a single variable of x, all we need to do is divide the whole thing by the derivative of the power. So our v is negative e to the negative 4x over 4. Now we simply algebraically solve and derive our integral expression, which is written below and being solved on the right-hand side here. And finally, we evaluate the antiderivative of our integral from 2 to 0 to find our total drug exposure over the whole surgery. This value is 2.43 milligrams times hours over liters. Next, we can visualize this function with a graph. The graphed function right here represents our drug concentration over time, and the shaded region underneath the function represents the value of the total drug exposure over our 2-hour interval. As we established, this value is 2.43 milligrams times hours over liters. Now, what does this mean? Well, in conclusion, one dose isn't enough. our total accumulated drug exposure fell below our minimum exposure threshold of 2.5 milligrams times hours over liter. This means that towards the tail end of the procedure, the patient would wake up if we only used one dose. And that's not what we want at all. Now, overall, it's great that as anesthesiologists, we did this math beforehand so we knew how to best take care of our patient and make sure that they didn't wake up in the middle of surgery. We can sleep well knowing that all we need is a little more than one dose of anesthetics to avoid torturing our patient and to avoid a potentially pretty bad lawsuit. However, despite this hyper-specific example of math and the mathematical concepts of integration by parts being used in the real world, I hope that this project has opened your eyes to how much we rely on math in our everyday lives and how reliant we are on it. So the next time you're sitting in class and you learn a seemingly obscure subject that you think you'll never use again, maybe think a little bit longer on how that can be applied to real life before you decide it isn't relevant. Thank you for listening and pursue math more and more every day.